First, I talk about the climatology driven by solar radiation and the deviations of the ionospheric morphology. We call those phenomena anomalies. And the anomalies are sort of the repeating phenomena. For like I use the different terminology, perturbations, to explain the irregularities, and like it is irregular, unpredictable phenomena. I will categorize the perturbations, and then I'll explain some of the phenomena, how we explain some of the physical processes of the phenomena. Let's see. The simplest thing that you can consider about the ionosphere is the sun is the source of the ionosphere, because the solar zenith angle varies with the latitude. You can think about day and night. There will be day-night variation of the density and latitudinal variation because the solar zenith angle changes with the latitude. And there will be seasonal variation, summer and winter, there may be difference. And solar activity varies with the 11-year solar cycle. There also will be a variation with the solar cycle. You can expect, without any background, ionospheric background, you can predict that kind of variations. Let's think about the production. Neutral density decrease with the altitude, and solar irradiance decrease with the decrease with the altitude decrease. So plasma density peak forms somewhere around 300 or 250 kilometers. And as I mentioned, you can expect day-night variation of the plasma density and solar cycle variation. And Sun-Earth distance vary. So you expect when the Sun-Earth distance is the farthest, the plasma density may be smaller compared to the season when the Sun-Earth distance is smallest. And also you can expect latitudinal variation. When sun is in the northern hemisphere summer, the plasma density may be higher than the southern or winter hemisphere. That's something you can expect from the solar radiation, but the ionosphere is much more variable that you can predict with the solar radiation. This is the swarm satellite observation at an altitude of 470 kilometers. This is northern hemisphere and southern hemisphere. You can see the two peaks occurrence in the equatorial region. We call that equatorial ionization anomaly, and also trough forms at the magnetic equator. And then plasma density enhancement here and trough structure here. And then in middle latitude, between the boundary of middle and high latitude, middle latitude ionization trough forms here, and between middle latitude and low latitude, the tropical ionization trough forms. This is the nighttime observation of the ionosphere. And also here you can see there's some very smooth plasma density variation, but there are also large fluctuation of the ionosphere irregularities. This is the one-day observation of a swarm satellite, and orbit by orbit, I plot the density plot here. This is a density and different orbit. This is the midnight observation. This is a noontime observation. In this plot, you can see many phenomena, occurrence of many phenomena in the ionosphere. First, you can see this density decrease here between the middle and high latitude. That's the middle latitude ionization trough. And equatorial region, there's plasma density depletion compared to the background. There's a plasma bubbles. And middle latitude, the fluctuation is very small, but there still exist irregularities. They are produced by middle latitude irregularities produced by traveling ionospheric disturbances. In the noontime, here you can see two peaks. There's the equatorial ionization anomaly and trough. And from this plot, you can see the large longitudinal variation, even though it is the same day observations. So ionization anomalies. As I mentioned, the deviations of the ionosphere from the prediction of photoionization effect we call anomalies. there are many different names of the anomalies: equatorial ionization anomaly, winter anomaly, annual anomaly, semi-annual anomaly, weather sea anomaly, and many. I mentioned the 3 types of troughs, and also there's longitudinal and hemispheric asymmetries in the ionosphere. So these kind of anomalies are not explained by considering the solar radiation effect. Let's look at some of the phenomena in some detail. This is a nighttime ionosphere. It's a timed GUVI observation of the ionosphere. Bright region represent higher plasma density, and GUVI instruments scan the ionosphere, and this is a one-day composite image, about 14 or 15 orbits of data. The equatorial ionization anomaly is formed to layer, and trough is along the magnetic equator. And this dark band, they are produced by equatorial plasma bubbles. I'll explain later. And this is the aurora. And this aurora is the most distinguishing feature in the ionosphere, but this equatorial ionization anomaly is also very distinguished feature in the ionosphere. Weather sea anomaly is the phenomena specifically in this region, weather sea area. If you compare the plasma density during daytime, this is the daytime observation, and this is a nighttime observation. Nighttime plasma density is higher than the daytime plasma density. So when this phenomena occurs in this region, we call weather sea anomaly. But this phenomena is not confined to this region. You can observe this kind of day and nighttime density difference in northern hemisphere and also southern hemisphere in other longitude regions. This plot shows the middle latitude ionization trough. This is the cosmic observation data. This is the nighttime. Blue color represent nighttime observations, and this is a daytime observation. And this is southern hemisphere, June solstice, so winter hemisphere. Okay? This is the winter hemisphere. You can see this layer of plasma depleted region. This phenomena is called middle latitude ionization trough. And if you go to lower latitude, this is the average density, longitude average density. This is the observation in December solstice. So this is summer, winter. In the winter hemisphere, you see the plasma density dip in this region. And this is May to August, so June solstice observations is summer and winter. So in the winter hemisphere at nighttime, plasma density trough forms between the low and middle latitude boundary region. I call them tropical ionization trough. This map shows better about the longitudinal variation. So this is a northern summer hemisphere, northern summer, so this is the winter hemisphere. You see this plasma density depletion here, trough structure. It is more pronounced than other region. And in these months, this is the winter hemisphere, and you can see also this layer of plasma depletion. Not plasma depletion, the trough structure. So trough structure is a seasonal phenomena and also nighttime phenomena. This plot shows the middle latitude plasma density observed by derived from cosmic observations. And this December is the northern hemisphere. December is the winter, and June is summer. If you compare the plasma density at noontime, December is greater than June. In other words, plasma density in winter, during winter is greater than June. So this phenomena is called winter anomaly. This is the radar observation at Millstone Hill, the same phenomena. Compare this to, at this time, the plasma density in December is greater than June. I also want to mention one more thing here. Compare this in June solstice. the plasma density at night is greater than that during daytime. As I told you earlier, weather sea anomaly represent the plasma density at night is greater than daytime, but that phenomena is not limited to the weather sea anomaly region. It appears also in the northern hemisphere and southern hemisphere. It's a general phenomenon in middle latitude. And this plot is the average density, longitude average density in low latitude. This is the local time, this is the month. The plasma density in equinox, okay? Equinox is greater than solstices. This phenomena is called a semi-annual anomaly. This is also a different view with a different observation. These plots were made using SWARM A satellite during 2014 and 16. As opposed to this northern magnetic north, magnetic south, this magnetic latitude 50 degree, 60, 70, 80. So it's a middle latitude and high latitude. If you compare in northern hemisphere, winter and summer, winter time plasma density is greater than summertime, right? That's the winter anomaly. The same phenomena in the magnetic south, winter is greater than summer. And also you can see compare the day and night, okay, summertime, nighttime plasma density is greater than summertime. Okay? So it's part of the weather sea anomaly phenomena occurs in the northern hemisphere, also in the southern hemisphere. And here I also mentioned that this plasma reduced region, this is the middle latitude ionization trough. This phenomenon is pronounced in the winter hemisphere. And this plot shows the CHAMP observation at an altitude of 400 kilometers. During the solar minimum period, this is a daytime observation. This is the June solstice, so this is the southern hemisphere, summer hemisphere. In December solstice, southern hemisphere is summer. So in the southern hemisphere, plasma density is greater than in the winter hemisphere. But during the solar maximum, in June solstice, the difference is not that clear. But in this December solstice, this winter hemisphere is greater than summer hemisphere. So there is some solar cycle dependence of the hemispheric plasma density. This plot shows the longitudinal variations of the daytime plasma density. This is the different months, different seasons, and this longitude is the same. This is average density between 12 to 16 local time. You can see the longitudinal modulation of the density, and the wave-like structure varies with a season. Here you can see wave number for structure in the seasons, but it is not that clear in December solstice months, January and November. So the phenomena so far I showed are some repeatable phenomena. At nighttime, you can expect the occurrence of the weather sea anomaly, and also you can expect creation of the equatorial ionization anomaly and middle latitude ionization trough. Those phenomena are sort of repeatable. But here, from now on, I'm going to talk about the phenomena that is not is repeatable, but it's event basis. Okay? For example, if magnetic storm occurs, the perturbation occurs, and plasma bubbles and traveling ionospheric disturbance are created when there's perturbations. It's not like irregularly occurring phenomena. So first, I use the terminology to describe a smaller scale and unpredictable variations of the ionosphere. And this perturbation, main cause of these perturbations are magnetic storms and plasma instability. And also, I want to show the perturbations associated, like earthquake, tsunami, tropical weather, tornado, and also man-made phenomena like rocket launch. this kind of phenomena also affect the ionosphere. Let's think about during the when geomagnetic storm occurs, how the ionosphere changes. This DST index is an indicator of the geomagnetic storm. So main phase start and recovery occurs later. And before the storm, the total electron content of the ionosphere look like this. And then as the storm progresses, this equatorial region plasma density is significantly increased. You cannot clarify in higher latitude, but there is also a change in high latitude. And as the storm recovers, the plasma density in the ionosphere is reduced even compared to the before the storm. So there's huge variation of the ionosphere, and this kind of variation depends on the magnitude of the geomagnetic storm. And this plot shows the DMSP satellite observation at 840 kilometer at evening terminator. The dotted line shows the before and after the storm, and this thick line shows the plasma density during the storm. If you compare the difference, it's about more than 100 times plasma density enhancement occurred in mid-latitude. And in the equatorial region, normally the morphology doesn't show trough at the magnetic equator, but during the storm, the ionization trough appears in the equatorial region. So huge change occurs during the magnetic storms. And this plot is to show the irregularity distribution. It's not related to the geomagnetic storm, just regular days, the distribution of the irregularities. In high latitude, the irregularities occurs most of the time, almost 100% time. This is nighttime observation of the ionosphere. In the equatorial region, because of plasma bubbles, you can see the irregularity occurrence. In middle latitude, the irregularity occurs less frequently than low or high latitude, but there still occurs irregularities by TID. If you curious about this plot, you look at the one-day observation of a swarm observation. In high latitude in this region, okay, you can see irregularities in all longitude region. In equatorial region, like the plasma bubbles here, produce this kind of irregularities. In middle latitude, it's not that clear here, but there's small scale fluctuations of the plasma density, and it creates the middle latitude irregularities. And there are different types of irregularities. This black line shows the total electron density. And if you draw a line, okay, the background line, compare the background line, you see the plasma density depletion occurrence. That's called plasma bubbles. In this region, if you draw the line background, the plasma density enhancement occurs. We call that plasma blobs. And there are places you cannot distinguish the bubble or blobs. I just call them irregularities. It's in the observation in low latitude by thin-up satellite. Equatorial plasma bubbles. Its structure is different by observations. When all-sky camera take a picture of the plasma bubbles, it can see it appears as a black emission depletion band, and actually the cameras only see part of this plasma depletion here. This is the three-dimensional structure of plasma bubbles, but the all-sky camera can only see this region. And when satellite pass through these plasma bubbles, you can see only one depletion here, okay? And when radar on the ground observe plasma bubbles, you can see only this structure at the magnetic equator, and this structure appears like this. This curved structure. When you take a picture from space, you cannot see the whole bubble structure. You can see only this line here, where the plasma density contrast background and plasma bubble is the largest. So only detect this one, and bubble appears like this curved structure. So it doesn't mean, so when you see the plasma bubbles in satellite image, well, it doesn't look like field line is something like that. It doesn't look like aligned to the magnetic field line. That's because you don't see the whole structure. You can see only the bottom of the bubble structure. This plot is shown to show that the bubbles are nighttime phenomena. So bubbles occur around 19 o'clock and it develops and then decay later. So it's a nighttime phenomena and also limited in low latitude region, mostly plus or minus 20 degree magnetic latitude region. And the occurrence of bubbles depend on the solar cycle. This is the F10.7 variation, the solar cycle indicator of solar cycle, and the bubble occurrence also shows the high occurrence rate when solar flux level is high compared to solar flux level is low. And this plot is the yearly observation data. So you can see the occurrence rate, occurrence pattern is very similar year by year, but as the solar cycle declines, the occurrence rate decreases, right? And this plot also shows the occurrence of bubble as large longitudinal variation and also seasonal variation. And why do we care bubbles? This is the top 10 science news story is selected one of the top 10 science news stories in 2014. And this story was based on this paper. The story is that in Afghanistan, the US helicopters fall down and the rescue team was sent to rescue these people, but they give wrong information. They go to the place where actually the helicopter was fall down. So they want to change different, ask them to go different places, but there were communication problem. So many people died by this communication problem, and they think this article says plasma bubbles may be the cause of the communication problem. But I don't know whether it's true or not, whether it's due to the plasma bubbles or what there can be sporadic phenomena can be the source. But this story may tell us why plasma bubbles are considered importantly. And that's the plasma bubbles phenomena in the equatorial region. If you go to the middle latitude, the most distinguishing phenomena is traveling ionospheric disturbances. Special type, special wavelengths, and special propagation speed. TID is called medium-scale traveling ionospheric disturbance. And this T is the total electron content perturbation maps in Japan and US. You can see this kind of wave structure. This structure is propagating west to southward, and also the same in the northern hemisphere in the United States. These are called MSTID. This plot shows the comparison of satellite observation and total electron content map. In Japan, you can see some fluctuations. These structures may be considered MSTID. When satellite pass through this region, you see the irregularity observed, and also here observed, and also it was observed in this region. But what I want to point out here is that when the TID occurs in Japan, is at the conjugate location. You see also similar structure, right? Here also, this conjugate structure. On this day, there was no TID. Japan is over here. There's no TID, and also at conjugate location, there's no irregularities. So this TID has very much a conjugate property. So once you observe in the northern hemisphere, you can expect observing similar structure in the southern hemisphere. This plot shows the distribution, MSTID, in the magnetic north and magnetic south. These observations were derived from Swarm A observation during this period. First of all, I want to say the similarity of the structure distribution. Okay? And also this monthly variation is not seasonal variation, it's more annual variation. What I mentioned, seasonal variation, is that if it is seasonal variation, if its occurrence is high in summer, it should be the same in the magnetic south, right? But here, in the summer, northern hemisphere, occurrence rate maximum, and the same in winter in the magnetic south. So it's annual variation, not the seasonal variation. And in this longitude region, this is a Asian sector. The TID occurrence is almost 100% during northern summer period. So this conjugate, this structure, similarity of the distribution and annual variation is a strong indicator of the conjugate property in MSTIDs. And now I'm going to show you some ionospheric disturbances associated with the natural phenomena. After the earthquake in Tohoku in 2011, this is the epicenter, and as time progresses, you can see the propagation of ionospheric perturbations, concentric structures, and this is a strong evidence of the earthquake effect of the ionosphere. This plot shows the typhoon effect. As the typhoon progresses, it also shows the ionospheric electron density change. This plot is after the tornado. After the tornado, you can see concentric structure propagating to a broader region. This one is related to the rocket observation. This is swarm observation, it's daytime observation. If this kind of plasma depletion observed in low latitude at night, you may think that this structure may be related to plasma bubbles. Or in middle latitude, you may think about TID, but this is daytime observation. During daytime, this kind of a plasma depletion is hard to observe in the ionosphere. And using this observation, we couldn't find the source of the depletion. After we look at the TC map, we can direct the TC depletion connected to the Kennedy Space Center here. So it may be, we thought that it may be related to the rocket launch, and we found actually on this day, the rocket launch was happened in Florida. And these observations are related to rocket launch from North Korea. This is the rocket launch place and launch this direction. And at the ionospheric pierce point of GPS satellite, you can see observation of TC depletion here. Okay? So you can use some, using the depletion magnitude, you can estimate the size of the rocket and the height of the rocket. This is a different observation of it. It is the same about after the rocket launch. Usually we thought that after the rocket launch, the plasma depletion, as I showed earlier, may occur along the satellite path, but this plot shows actually the concentric perturbations of ionosphere occurring by the rocket launch. Okay. So I told you so many, you cannot remember all the phenomena, but I want to show you the kind of variation occurring in the ionosphere. And I want to talk about how can you explain some of the features, not all of them, but some useful physical processes in the understanding ionosphere. I'm going to talk about that. The time variation of plasma density in the ionosphere can be described by the production, loss, chemical loss, and transport. Okay? The anomalies in the ionosphere is related to these terms. And you can model the production. If you know the solar radiation, you can model the ionosphere. This is a Chapman layer, depending on the solar zenith angle. If the zenith angle is small, you can have more ionization, but as the angle increases, the ionization decreases and the height also increases. The ion's plasma is a very small constituent in the ionosphere compared to the neutral density. It is thousands of times smaller. So the plasma in the ionosphere is affected by neutral particles. And the ionosphere main constituent is O+. This is O+ constituent. So majority is O+ ion. Low altitude, there's molecular ion, but mostly we think about the O+ ion in the ionosphere. So the increase or decrease of plasma density in the ionosphere is related to the production and loss of O+. Production is ionization. Loss process can be various. One is direct recombination. The other way is dissociative recombination with molecular gases. Okay? One makes very complex is this process here. Let's explain this. I compare the plasma loss related to the dissociative recombination and direct recombination with electron. I used the O plus density and N2 density around this altitude. If you compare about 200 or 250 kilometers, this process is about 1,000 times faster than this process. So plasma loss by chemical reaction is dominated by this process. It means that the neutral gas population in the ionosphere is very important in plasma density. Let's think about the situation. Let's assume that this is O plus density. This is the N2 density. Let's assume somehow the ionosphere is lifted higher altitude like this one. Then at this altitude, neutral density is very much reduced. It means that this process occurs less, and therefore its effect is plasma density enhancement compared to this process. If the ionosphere is lower down, and then there is more neutral gas density, and this process occurs more frequently, then it causes the plasma density decrease. So higher altitude means is positive effect plasma density, and lower altitude means the negative effect in the plasma density. So height is very important in the ionosphere. Then how can you change the ionosphere height? One way is, this is the magnetic field line. Plasma is tied to the magnetic field line. If the neutral particle collide with ions, it can move plasma along the field lines. Okay? Direct collision can move the plasma up and down, and by that way you can change the ionosphere height. The other way to move electron plasma to perpendicular to the magnetic field line, you need electric field because its gyro motion is not easy to move. So if the electric field move this or this direction, okay, it can also cause the plasma density enhancement, and this movement can plasma density decrease. So either electric field or neutral wind, direct collision with neutral wind can change the ionosphere height. And then how the electric field generated in the ionosphere. Let's assume neutral particles is moving this way. There's ion and electron, and there will be collision. Then ion and electron does not move together. They move differently. Different move develop current. If the current is higher in the high wind region than smaller wind, then current flow small and more, then negative charge accumulate here, then it creates electric field. Then this electric field can move the ionosphere up and down. Or let's assume the neutral wind is uniform, but the plasma density is different. It can be daytime, higher density, and low density in nighttime. Then neutral collision, neutral particle collision makes more current flows in the high density region than low density region. Then again, electric field charge accumulate, then electric field again generate. Okay? This is the important in low and middle latitude, but in high latitude, external electric field is important source. Let's assume plasma solar wind particles moving against magnetic field. Then by Lorentz force, they are deflected. Then deflection makes at the boundary positive and negative charge accumulate. The electric field develop. This electric field map down to the ionosphere, and this electric field can move plasma horizontally. The difference in high and low middle latitude is that in high latitude, this electric field just move the plasma in horizontally, not vertically, right? Because magnetic field is perpendicular to the surface. So in the high latitude, horizontal movement is important factor for the creation of disturbance in the or irregularities in the ionosphere. You can assume that electric field may move day side plasma to night side, and the mix of day and night plasma can make the irregularities in the high latitude. And the other thing to consider in low latitude is that Fregion that you're interested in is connected along the magnetic field line to the E region. So if the electric field develop here, this electric field can affect the plasma motion in the F region. And let's just to idea, I explain this one. This is the magnetic field line. This is the magnetic equator. Let's assume this is about 10 degree magnetic latitude, E region. This E region is connected to the F region along the magnetic field line. The current in the ionosphere, driven by neutral wind, is described by this relationship. Let's assume that wind blows from equator to higher latitude, okay? Then this wind derive current, this current here. Current, day side plasma density higher, so more current flows than night side. It's less current, more current. Then it develops positive charge accumulate here and negative charge accumulate here. Then electric field develop, and this region electric field, this magnetic field is northward. This magnetic field is mapped to the F region, and this electric field drive E-cross-B drift of plasma. This is by the gyro motion of plasma, upward plasma motion. Using this information, you can see dawn positive charge, dusk negative charge, electric field develop this way. Then this electric field move plasma upward during daytime and down at the nighttime. Then this upward plasma motion induced the plasma diffusion along the magnetic field line. And then by this process, we call fountain effect, plasma density maximum occurs not the magnetic equator, but a little bit higher latitude, plus minus 10 or 15 degree magnetic latitude. We call these structures Equatorial ionization anomaly. And the longitudinal structure, this is observation, daytime of plasma density. I showed that there's longitudinal variation of plasma density, high, low, high density. And this kind of structure is related to this vertical plasma motion. Okay? This is the model simulation result with the vertical plasma motion. And using this one, we can reproduce plasma density enhancement in the region where the vertical plasma motion is high and small when the vertical plasma is low. Similar is observation and GIP model simulation. Using this kind of vertical plasma motion input, we can reproduce a similar longitudinal variation of the plasma density. So vertical plasma motion is very important, and the vertical plasma motion is not uniform with the longitude. It can be caused by like a tidal effect or other factors, and then this vertical plasma motion difference can produce this longitudinal variation of plasma density. And let's think about the neutral wind effect. There's sunlight, and then the wind blows from the equator region to higher latitude, right? So when wind blows this region, the magnetic field line is something like that. Then this wind pushes ionosphere to lower altitude during daytime. But at night, wind pushes plasma upward. So this upward motion is positive effect in plasma density. This downward motion is negative effect in the plasma density. Well, let's think about, this is the equinox, but let's think about the June solstice. Sun is here, the wind may blow this direction, and this is the terminator. I mean, this area is still sunny side, right? Even though the time is nighttime. So wind is blowing equatorward, and it pushes ionosphere to higher altitude. But still, sunlight make ionization at nighttime. Okay? So it can cause the plasma density at night can be greater than during daytime. Because here, still during daytime, as I showed here, neutral wind pushes down the ionosphere. But at nighttime, neutral wind pushes up the ionosphere, so positive effect. Moreover, in the summertime in the northern hemisphere, sunlight still making ionization, so the plasma density can be higher during nighttime than in daytime. So this may explain the weather sea anomaly phenomena. This plot is to explain why the trough tropical trough appears in at the boundary of the low and middle latitude. Let's assume June solstice, wind is blowing. Okay, there may be convergence occur somewhere here. So in this region, in the northern hemisphere, neutral wind pushes up the ionosphere, so positive effect in plasma density, but here is pushing down the ionosphere by wind. So it's negative effect plasma density. On the other hand, at higher latitude, solar wind is pushing up the ionosphere, so it maintains the plasma density. So that cause the plasma density drop in middle latitude here. In addition, then why there is a longitudinal difference of the in the intensity of the drop? Here more pronounced drop than compared this region, and also here than the other region. You have to think about this, not only this meridional wind, you have to think about the zonal wind. Magnetic field line in this longitude region is slanted like that. This region is slanted like that. Assuming summer, meridional wind is blowing summer to winter this way, okay? It has a component along the magnetic field line. On the other hand, the nighttime zonal wind blows eastward. This wind has component along the field, and this component is against each other, right here. On the other hand, here, zonal wind is the same direction as this direction. So these two components are the same direction. During the summertime, and during June solstice in this case, in this region, the pushing down is more significant in this longitude region than this longitude region and other longitude. So it appears more severe. During December solstice, wind is the other direction, even though the zonal wind is the same direction. So it happens in this longitude region. You can apply the same logic in this region, then you can explain why it happens more, why the more severe drop occurs in this longitude region. Okay? This magnetic field configuration is an important factor for that. And let's think about neutral composition effect. I thought about just ionosphere height variation, but you also think about even though the ionosphere height is the same, the neutral density can change. One way is the heating of the atmosphere. For example, the ionosphere is the same, but somehow let's think about the atmosphere is heated by geomagnetic storm. Then at the same height here, now the neutral density, N2 density is greater than previous. So the increase of N2 density caused a negative effect, reduce the plasma density. So you can reduce the plasma density. Okay? And for the winter anomaly is the phenomena, the plasma density during winter time is greater than summertime in middle latitude. In summertime, there's more solar radiation and there's more ionization, but at the same time, the solar radiation hit the atmosphere. It expands the atmosphere, right? Expansion of atmosphere can increase the molecular gas density in the ionosphere. So this effect also have to be considered. So you cannot just simply explain by the solar radiation, the ionization or neutral wind effect. You have to also think about the neutral composition change can affect the plasma density. During storm time, let's assume this in the high latitude there's convection pattern. Okay, it's not always. I just assume two-cell pattern in high latitude, and this convection is caused by the electric field driven by solar wind and magnetosphere and this plasma motion. During storm time, this convection pattern extends. For example, the solar wind-driven electric field is much larger than this effect. The convection pattern increase, and this effect can expand to lower latitude. Okay? Not previously, it was confined to high latitude, but during storm period, it can be extended to lower latitude, and this electric field can affect the up and down plasma motion, and this electric can uplift ions at very high altitude, and in equatorial region, it can produce this kind of a trough structure that does not appear during quiet time. And neutral wind effect, we can also think about. Wind, as I mentioned, the wind blows from sun from the day side to night side and high latitude. And during magnetic storm, the heating occurs in the auroral region. This heating causes wind. Okay, this wind is against the sun-driven wind here in the day side, but in the night side, solar-driven wind and auroral heating, storm-driven wind is the same direction. So this wind effect is the uplift of the ionosphere, and this kind of severe wind effect can cause this type of high plasma density enhancement of 100 times, more than 100 times. And there's some abrupt decrease in plasma density here. Maybe the auroral region heating enhance the molecular gas density in the ionosphere by heating expansion of the neutral atmosphere, and then it caused the plasma density, suppression of plasma density. So it may create this kind of steep boundary at the subauroral region. And I told you many phenomena related to earthquake and tornado and tsunami, and this kind of variation can be explained by the gravity waves. Let's say the wind blows through along to the mountain, then the wave structure in the atmosphere may develop. We call it gravity wave. Or earthquake, tornado, volcano, or rocket may also produce the wave structure in the atmosphere. And auroral heating also, and hurricane. This kind of gravity waves modulate the ionosphere. And the modulation of the ionosphere, density, height and density, provide a preferable condition for the development of instability. Let's assume in this case, let's the ionosphere modulate something like that, then current flows in the low density and high density. The current is different, the magnitude is different, and then charge accumulate here, and then electric field develop, and this electric field can move the ionosphere up and down motion, and also secondary plasma instability. By this process, the atmosphere or this kind of phenomena can affect the ionosphere, and ionosphere affect the plasma density in the ionosphere. Yeah, so far that's all I want to say today, and I prepared to a few topics that we can work with the HAO modeling scientist. Well, here I explained that the trough is most severe. Tropical trough is severe in this longitude, but it's just a speculation. Okay, explain this way, but models may test whether they can reproduce this kind of structure. And this is the hemispherical symmetry, solar minimum and solar maximum. There is some difference in the symmetry here. So, well, this kind of phenomena may also be tested by model simulations. Well, I talked with before I talked to this seminar, I talked with Alan Bunce about whether we can do TID simulation using TIGCM, but the resolution is not good enough to produce TID. But what I'm interested in is that why the TID occurrence frequency is higher in the Asian sector compared to other sectors, and why it shows the annual variation, but not seasonal variation. It may be explained by the conjugacy, but then what caused what initiate the TID, and there's study that this TID production is related to sporadic E. If you look at the sporadic E distribution as a function of longitude, sporadic E is the abrupt plasma density enhancement in the E region, and this abrupt plasma density enhancement in E region caused the instability in the E region and map to the F region, it perturbs the F region. That's some explanation. If you look at the sporadic E distribution as a function of longitude, the occurrence rate is higher in the Asian sector than other longitude sectors. So one reason may be the sporadic E, maybe the reason for the creation of a traveling ionosphere disturbance, but TIGCM cannot simulate. But semi-model. I don't know whether you can do. Joe is here. Okay, that's all my presentation today. Thank you.
Okay, so thank you very much for a very nice and comprehensive presentation on ionosphere, climatology, and disturbance. So questions? Yeah. So do you have any observations that shows the winter anomaly that has a longitudinal variation?
Oh.
Yeah.
I think that there's some previous study, 1970s. There's some study, but I think there's some study, but like recently I didn't see. For the recent data, we didn't look at, and I cannot remember recent study.
Oh, okay. Okay, and so what about the this ionosphere variation? You know, this looks like a wave that caused by like a rocket launch, tornado. How much like a delay? Like when there's like a tornado, and then how much time it takes?
If you see I didn't check the time, but the earthquake, after the earthquake, I think it is quite immediately, about some tens of minutes, 10 minutes or 20 minutes, the perturbation appeared in the ionosphere. And also rocket launch about 10 minutes after the concentric structure appeared, I think.
You did mention the tsunami also. The 2011 tsunami was very clearly seen traversing the Pacific and the ionosphere.
Not shown here, right? But yeah, I know that, yeah.
It's a very interesting effect. Yeah. My question, though, was if you could have, given the observations you have now from, it looks like mostly NASA satellites, what would you like to have in the future? What's your ideal observing constellation for ionospheric studies?
So whether you observe perturbation in the ionosphere, you can use it as a warning of the tsunami?
No, just in general for research or studies.
Well, I think the tsunami, I don't know, for the tsunami, I know the movie that propagation from the Japan to United States.
That was GPS. That was all ground-based GPS.
I don't remember any observations, detection of tsunami signature in the ionosphere and the satellite observations.
My question is about not tsunami, just general ionospheric research. What would be your ideal observation constellation of satellites and
constellation.
Yeah, what would you like to see in the future for better observations?
I don't know, as many satellite observation may be better, but there's some, I don't have clear idea what is the best option, whether you have to think about which orbit is best to impact, is equatorial or polar orbit, and how many satellites. It depends on as many satellites, it will be much better than less.
Maybe 1,000 CubeSats is better than one.
You know, even though 1,000, if you think about the coverage, it's not that much. If you one satellite, your location just pass like twice a day, but if its gap is like 25 degrees, so exactly your location is very low, even the polar orbit satellite. So even 1,000, I don't know, 1,000 coverage for your location is global coverage. 1,000, there can be never enough, right? You can do better, but.
So what are the mechanisms that, I mean, what is the physical process that cause, you know, when you have a tornado, then cause ionosphere variation? You know, what is the process?
Fundamentally, the impact, this explosion, it's the same as a nuclear bomb explosion, rocket launch, okay? It impact the atmosphere, and then this gravity launch and this gravity wave, I don't know whether it directly propagates to the upper region or it propagates somewhere and break and secondary gravity wave generate, but then maybe the reason that the gravity
wave.
Yeah, that's most people explain, is it?
Causing ionosphere disturbance. It's always look like it's decreasing in electron density? Why it's
One thing is, one is a concentric
yeah, those
structure is more gravity wave launch from the center, it propagate. But the decrease of plasma density is because the exhaust, there's a H2O and it react with the plasma, it reduces the plasma density.
I saw that you measurement, you through the swarm or no, some satellite, it seems like pretty high, it's more than 300 kilometers, but I saw the rocket doesn't go high.
Rocket goes, North Korea can launch that
rocket
high.
really goes that high?
Yeah, it goes to even recently 1,000 kilometers.
Oh, really? Oh, okay.
Any questions? Yeah. So, okay, so let's thank our speaker again.
Okay, thank you. Thank you for listening.